Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by COMSOL, Chemical Reaction Engineering, Modeling, and Simulation in COMSOL Multiphysics. Our speakers are Ed Fontes and Jennifer Seggi. Ed Fontes is the Chief Technology Officer at COMSOL. He has been with COMSOL since 1999 and was previously the lead developer for the CFD heat transfer and chemical engineering products. He received his PhD in chemical engineering from the Royal Institute of Technology, Stockholm. As a senior technical marketing engineer at COMSOL, Jennifer Seggi writes and produces demos, presentations, articles, and documentation showcasing the capabilities available across the entire COMSOL product suite. She's also the program co-chair for the COMSOL conference in Boston. Jennifer has degrees in medical physics and computer engineering. One quick note before I turn the session over to Ed Fontes and Jennifer Seggi. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Ed Fontes and Jennifer Seggi. Hi, Ed and Jen.
Thank you, Pam.
Hi, Pam.
All right, so Ed, if you wouldn't mind advancing to the next slide, we'll move right along with our agenda for today.
There you are.
So we'll begin with an introduction to simulation and more specifically modeling and custom application design with COMSOL Multiphysics. You'll learn about some of the tools that are available for modeling transport and reactions as well as heterogeneous catalysis. Ed's presentation also discusses modeling strategy and includes a live demonstration in COMSOL, which shows how to set up a model of heterogeneous catalysis. Finally, there's a Q&A session followed by a brief how-to. Again, we would like to encourage you to continue sending questions to us. You don't have to wait until the Q&A session starts. All right, so I'll go ahead and turn the presentation right over to my colleague, Ed.
Thank you, Jen. Pam, I'm not able to advance the slides.
Okay, Ed, there you go.
Now it works. Thank you.
Okay.
So let's start by asking ourselves a question: why simulate reacting systems? We ask this because traditionally this type of simulation has been quite limited in the chemical engineering education. But it has been a lot of relying on experimental and empirical results to govern the design or the studies of a reacting system. And if simulation has existed, it has been to simulate in 0 dimensions, basically, only accounting for the evolution of the reacting system as a function of time. But as simulating tools and computational power has increased over the years, simulation has been attainable for all chemical engineers, also high fidelity simulations. So first of all, simulations or modeling, mathematical modeling and simulation, the first step is that it provides an understanding of the different parameters that make up your system and how they affect each other. And with this understanding comes intuition that leads to new ideas and that allow you to take big steps forwards in the development. And so modeling and simulations let you propose some design and conditions, and then it allows you to tinker with them and optimize them. And a lot of this can be considered and achieved before proceeding to expensive pilot plants. You can stay in the lab for a longer time before you start building prototypes and deploying to manufacture, going to the full scale, for example. And of course, it also lets you propose the full-scale design. Once you have working understanding and once you have improved your model at the lab scale, you can adapt the process to different operating conditions or the reacting system, study it at the full scale. And in some cases, if you're dealing with a process, it also allows you, of course, to optimize it. And sometimes you need to know what would happen if, for example, an accident happened in a plant, or if an accident, for example, would happen in a casino, like one of our users experimented with. What would happen if there was poisonous gas in a ventilation system with reactions and so on. And a real-life experiment could be difficult, if not dangerous sometimes. And simulations can provide a decent estimate of what could happen in a very inexpensive and relatively inexpensive way. But of course, the real world is not simulation. So you have to work together with experimentalists, and you have to validate the models in order to use them for real studies. And so that's also a tool that we include in the COMSOL chemical reaction engineering products. Is a way to perform parameter estimations and a very efficient way to perform validation of your models with experimental results. So if we start by looking at the product suite of COMSOL in version 5.2a, you see there are a lot of modules, but they all share one common denominator, and that's the mathematical engine of COMSOL Multiphysics. So actually all the physics-based products that we call modules, they share the same type of equation formulation under the hood. And so the chemical reaction engineering module, it presents a number of graphical user interfaces in order to model reacting systems, such as chemical reactors, or studying basic studies of heterogeneous catalysis, and processes with transport and reactions, also including fluid flow. If you need to include turbulent flow, or multi-phase flow, then you would use the chemical reaction engineering in combination with the CFD module or the mixer module. Then we have more specialized products for modeling of batteries and fuel cells, which actually is an applied branch of chemical reaction engineering. I myself studied chemical reaction engineering with the special branch of applied electrochemistry. And the same thing, we have the electrodeposition module, corrosion module, and the more generic electrochemistry module. Less generic than the chemical reaction engineering module, but more generic than the other electrochemical products. And for transport phenomena, like I said, we have the CFD module, where you are, maybe some of you listened to the presentation about reacting flows, which is similar to this one, except that in this presentation I will go more into heterogeneous catalysis and homogenization. But then you also saw the CFD module in action, where we model reacting flows, and also in the mixer module, the microfluidics module that includes some type of fluid flow models and transport models for microsystems, subsurface flow module, which can also be used in conjunction with chemical reaction engineering combination for porous media flow, multi-phase flow in porous media, and so on. The pipe flow module, which is able to connect different unit operations. For example, if you model several reactors connected with pipes, then you are able to estimate the pressure losses in the pipe and in the pipe system and so on. And then last, we have the molecular flow module, which is a module for modeling very low pressure systems. So the product chart in the preceding slide includes functionality that describes modeling of mass, momentum, and energy transfer involving chemical reactions. And the phenomena are also represented in this chart. And you might recognize the categorization here, which is familiar to all chemical engineers that studied the book Transport Phenomena by Burt Stewart and Lightfoot. And the phenomena mapped here form the backbone in the modeling of reacting systems in combination with transport, with fluid flow, heat transfer, and so on. So the structure described by mass, momentum, and energy transport phenomena together with chemical reaction is also reflected in the list of transport and reaction interfaces in COMSOL's chemical reaction engineering module and in combination, for example, with the CFD module. And this list is a snapshot from the model wizard in COMSOL in the step where you select the phenomena that you might want to include in your model. So here you can select from transport interfaces to model multi-component transport and reactions, single-phase and two-phase flow, surface reactions or homogeneous reactions, laminar and turbulent flow, heat transfer, with conduction, convection, and radiation, for example. And then a specific chemical species transport interface, the reaction engineering interfaces, is able to generate mass and energy conservation and transport equations from chemical equations that you type in almost like using pen and paper, and I will demonstrate this later on. A typical modeling strategy, or maybe an ideal modeling strategy, is to start the analysis of a reacting system using perfectly mixed systems, and those are usually the systems that you have in the lab. So a space-independent model with respect to concentration and temperature is a good way to verify and validate the reaction mechanism that you want to study in combination, maybe later on in combination with transport. So once the mechanism is validated and verified, models with concentration and temperature distributions also in space might be investigated. So we go from studying systems as function of t, time, to studying systems as function of time, x, y, and z, for example. And so you might calibrate and compare your model results to experimental data from lab scales experiment with very controlled composition and temperature. And you might actually use COMSOL to run parameter estimation, and that might give you a good match if providing that the mechanism is the correct one, and that you have covered a representative range of operations. And so you might also be required to run parameter estimation for transfer properties in high fidelity models, for example, in porous media or for turbulent flows. And in addition, if a simplified space model is used, further calibration might be needed for these simplified model parameters. And in some cases, one might discover that the range of operation in space-dependent models is not covered by the trials for the perfectly mixed system. In such cases, we might be forced to go back to the lab. So an almost opposite strategy might be implemented for the study of heterogeneous catalysis. I mean, nowadays with the ability to take microscans and produce 3D geometrical descriptions from microscans, we can now use these geometrical descriptions in detailed 3D models of catalyst particles or catalysts at the microscale. And those detailed models can be used for homogenization in order to model a larger number of particles. And as you know, if we have to model a larger number of particles in a unit cell, in a fixed bed or a packed bed, or a porous media in general, we cannot afford a detailed description. So a large number of particles can then be used to describe a unit cell or a packed bed reactor, monolithic reactor, or fixed bed reactor. And the homogenized particles model might also be used in fluidized bed models, for example. But let me start with a little example. Those of you that listen to the Reacting Flow webinar, this is actually the same example, but I will not take it that far because I want them to go to an example of a heterogeneous particle and a homogenization of the heterogeneous particle. So I will just show you how to type in chemical mechanism into COMSOL Multiphysics. So we will model a reacting system that includes two reactions. One desired reaction, A plus B gives C and D, and then a parasitic reaction is D plus E gives F and G. And I will just very quickly show you how to go from a 0D model. So we will set this up as a space-independent model, and then how we go from a space-independent model to a space-dependent, full space-dependent model. So now we'll try to share my screen here. And then I will try to go to the So I hope you see, Jen, do you see the model wizard now?
Yes, looks good, Ed.
Excellent. Okay. So this is the first step in the modeling procedure in COMSOL. So we start with the model wizard. We click in the model wizard, then COMSOL suggests the space dimensions, 0D, 1D, 1D axisymmetric, 2D, 2D axisymmetric, and 3D. And so we will start with a space-independent model. And we have a list of different so-called physics interfaces, which, like I said, they're user interfaces, graphical user interfaces adapted for a specific subject, for example, to model electrical circuits, to model reaction engineering, to model batteries, but also pure math interfaces where you can type in, since we're now modeling 0D, what we can type in here is our ordinary differential equation and differential algebraic equations. If we would have used 1D or 2D or 3D, then we would have also a bunch of partial differential equation interfaces where we could type in partial differential equations in the strong or weak form, for example. And then last, we have some 0D interfaces for optimization and parameter estimation and sensitivity. But we want to use the reaction engineering interface, so we select that, we add that to our model. And here we could, if we had a multiphysics model, we could continue adding in physics interfaces, but now we're just going to model a reacting system. So we go to the study, and in the study we could model a stationary system or a time-dependent system. So we will select the time-dependent system, and of course you have other custom studies that you can use. So we select the time-dependent study, and we we click Done, and then COMSOL prepares the user interface for this specific subject that we selected, reaction engineering. And so the modeling process is from left to right. And so the home tab here contains, well, actually shows the workflow in using COMSOL Multiphysics. You might set up parameters, variables, and functions. You might add components, and you might also draw a geometry. Now in 0D, this is grayed out because there's no need for a geometry. It's just a point. You might add materials, and you might access the reaction engineering physics interface. You might add other physics interface. There's no need for a mesh here because we're modeling 0D, so there's no mesh needed. But we can compute the study and so on. So a summary of the workflow is contained in the home page. But then the tabs here also contain, they also depict the workflow. So we have definitions to set up variables and parameters. We have materials to set up different material properties. And we have the reaction engineering interface, which is where we set up our problem. So what I will do now is I will add a reaction. And I do that by clicking in the ribbon, just clicking reaction. And here I can just type in A plus B gives C plus D. And I can select what type of reaction I want. And I want a reversible reaction. And now we start by modeling an isothermal system, but we could have used an Arrhenius expression with activation energy and so on in order to model a non-isothermal system. So I just type in the rate coefficient here, 10 cubic meters per second per mole, and the reverse rate constant 2 here. So that's for the first reaction, and we can set up the second parasitic reaction. And you remember that consumes some D by reacting with E and gave F plus G. And also this one, we want it to be reversible, but then with a slightly lower rate constant like this. And then what we now need is to have the initial values for this problem, for this set of reactions. So in order for A plus B, for the first reaction to start, we need some A and we need some B. We don't need some C and D because having A and B will start the reaction. But for the parasitic reaction, we need some E. And so we put some concentration there, initial concentration. And then if we look at the time-dependent study, it goes from 0 to 1 second. And so that's okay. So we go to the study here and we click compute. And hopefully, if I did everything correctly, we should get the concentration profiles as a function of time. And so we can see here that this is the green line here is A plus A or B, and it decreases in a monotonous way. We also see the production of C, which increases in a monotonous way. But the species D, which is in light blue here or almost turquoise, we can see that it increases initially and then passes through a maximum to decrease and then to flat out towards equilibrium. And that's because it's consumed in the parasitic reaction, and that's slightly slower. So initially, we have to produce some D in order to get any substantial rate of this reaction. And so we can see here that we get then the production of F and G shown by the black line here. And so if we go back to reaction engineering tab here, so now assume that we're satisfied with this. What we could do is, of course, to add a parameter estimation study. If we had experimental data, we could have tested, validated this mechanism, A plus B gives C plus D, and D plus E gives F plus G. And in the application library, we have examples, with 50 reactions, and so you can perform this type of study with a large number of species and reactions, of course, and also run parameter estimations. But assume that we were satisfied with this, we could actually click the Generate Space-Dependent Model, and this will add a node for generating space-dependent model from this reaction kinetic mechanism. And this would, for example, allow us to set up a transport of dilute species, and also, for example, to set up a laminar system for laminar flow. And once I create that, then COMSOL will automatically generate the physics interfaces required for this, and it will also create a first geometry. So now I have two model components in my model. One 0D, which is the study that we just set up, and then a second one which includes a geometry, and I mean that could be anything, of course. That could be, for example, if we were studying a catalyst particle, that could be a sphere, and that will set up the transport of diluted species in that sphere. And also, if we had some laminar flow around that sphere, that will set up that too. But we will not go into details with that. I'll continue assuming that this is. I mean, this is basically, there's some physical work to set this up, but other than the principle is exactly like I pointed out here. Just from your reactions, set up the fluid flow problem and the mass transport problem, and you're there, basically. Okay. Jen, can you see my screen?
Hi, Ed. Yes, it looks good.
Okay, excellent. So I'll try to go back and stop sharing. All right, now we're back to the slides. So Jen, am I okay here with the slides? Can you see the slides?
Yes, now you're on the slides.
Okay, so now we have, here is what we actually did. So let us recapitulate the modeling procedure. As we all could see in the demo, setting up a space-independent model is very straightforward. Just type in the chemical equations, and the species list and the material balances for each species are automatically formulated. What I didn't show is that the reaction mechanism assumes the mass action law, but you can actually edit that. So you get an analytic expression for the reaction mechanism as a function of the concentrations, and so you can edit that, like you do with pen and paper. You can type in any expression for your reaction kinetics, and then of course you can from this you can set up the space-dependent model like I showed. So these are formulated automatically by clicking the Create Space-Dependent Model. So let's now take another, well, let me just switch. Yeah, and what I didn't show was the ability also to perform parameter estimations, which is also exemplified in the application library in COMSOL Multiphysics. And I show you in principle how to extend to space-dependent models. And now we'll jump to the example of the modeling strategy for heterogeneous catalysis. So assume that we set up a similar system that we did in this little example, and now we want to model a catalyst particle. So the figure here shows the transport and reaction mechanism that could take place in a catalytic particle. So you see in circles, you have numbers for the subprocess. They're really small, I realize that now. But one is the transport from the bulk of the solution to the mouth of the pore. So that's the first step. And so that's the blue little molecule of A diffusing to the mouth of the pore. 2 represents the transport in the pore to the catalytic site of the reactant, for example. And 3 is the absorption of the reactant to the catalytic site inside the porous particle. 4 is the formation of the product, for example, and 5 is the desorption of the product from the catalytic site. 6 is the transport of the product in the pores from the catalytic site to the pore mouth, and 7 is the transport of the product from the pore mouth to the bulk of the solution. And so this is naturally described by COMSOL Multiphysics if we had set up the system correctly. So if you look at if we look at this slide here, the geometry is for the full heterogeneous model is at the top left in the slide. So this is a hypothetical geometry drawn in COMSOL, but it could very well have been a description from a microscan. So in the top middle image, the detailed geometry of the particle has been replaced by a homogenized porous particle. And the geometry of the particle is now described with a porosity, a tortuosity, and a specific surface area of the catalytic surface. That is area per unit volume, specific surface area. So once validated against the detailed model, the homogenized particle model might be used to model a larger number of particles in a unit cell of a packed or a fixed bed. This is shown in the top right image here. And then at the bottom, we see a second homogenization that can be made. The unit cell at the top right can now be used to describe a model porous bed in which the particles and the void between the particles is described as a single porous slab, but with a bimodal pore structure. This implies that the void between particles is treated with one porosity and tortuosity parameter, while the pores inside the particles have other values for porosity and tortuosity. So that's called a bimodal pore structure. And this functionality of treating catalyst particles at the microscale and at the same time model a packed bed or a fixed bed in the full scale, that's included in the new version of COMSOL Multiphysics of the reaction engineering. So it allows for the description of these completely separate modeling scales. And they're of course, these two scales are fully coupled. And where they are coupled is actually, if we go back, it's at the mouth of the pores. So at the mouth of the pores, the concentration is shared between the micromodel and the model of the fixed bed. And so if I share my screen again, and I hope you can see now I have the catalytic bed, the catalytic particle here. So it's a fairly complex geometry now. Actually, I have drawn this in COMSOL. And so if you look at the reactions here, they're surface reactions. They take place at the blue surfaces here. And here it's a very simple reaction. It's a linear reaction kinetics. And what I've done now is exactly what I showed you in the space-independent model when we click the Create Space-Dependent model. That I set up a laminar flow around the particle, in the domain around the particle, and inside the pores in the particle, and also transport of diluted species everywhere, of course, too. And that results in a concentration distribution and a fluid flow both inside the particle and around the particle that we might use to set up a homogenized model of a single catalytic particle. So let me just switch to another model. So this is exactly the same size and geometry, but now the particle is described with a porous media, as a porous media. And so we have free and porous media flow. We have the fluid properties, and the porous matrix is only defined in the particle itself, while the transport of diluted species is defined everywhere with some porous media transfer properties, like I said, a porosity and a tortuosity, and given by, in this case, it's actually Millington and Quirk model that you see down here. So there are different models for porous media flow. And that results in exactly like before, a concentration distribution and a flow distribution, both inside the particle and around the particle. Now the flow is porous media flow. In the previous model, it was actually free flow, but in very narrow pores. And here it's an effective model. And the same thing with the reactions. Now it's transport and reactions in a porous media, in a homogenized slab inside the spherical particle. And then we can take that a step further by including a number of these particles in one unit cell. And once we have that, we can actually step up, take the second homogenization step, and then this is exemplified. Actually, this is a model from the application library in COMSOL, where we set up the reaction kinetics in 0D, and then define the fixed bed here. So the fixed bed rests on a perforated plate at the bottom. So we can see the inflow conditions here at the bottom. That's in the perforations in the perforated plate where the fixed beds rest upon. And so between the perforations, there are actually no feed of reactants. And so at the top, we have the outflow. And in every point in space, we have these spherical particles. So this model is actually four-dimensional models, but the fourth dimension is in a completely different scale. So it's at the micro scale, while X, Y, and Z, they're at the macro scale of the fixed bed. So this is a bimodal porous model that I mentioned previously. And so now the reactive pellet bed is discretized with a separate fourth variable that represents the radius of the particle, and which you can input exactly like before, the average radius of the particle, the porosity and tortuosity, and so on. And you can automatically convert surface reactions to this type of reactions in a homogenized particle reaction diffusion process, or reaction transport process in this case. All right. So let's go back to the presentation. So Jen, can you see my slides now?
Not yet.
Okay, Pam, please. There we are.
There we are. Yep.
So we could go from a fully detailed 3D model at the microscale of heterogeneous particles to a homogenized model still at the microscale of the particle that's in the middle here, to a unit cell or a porous catalyst, including a larger number of particles, but still a unit cell. And then we can homogenize a second time that unit cell to a bimodal pore structure, which is the end result here. And that second homogenization, well, we have that type of interface in the new COMSOL reaction engineering module, where we basically in 3D, it includes 4 independent variables, which are the X, Y, Z, well, T too, and then the radius of the radius of the particle, which is at a completely different scale. Another thing that you might be familiar with is the new application builder we introduced. Well, now it's not that new anymore. We introduced that a year ago. So the models that we created now that I showed you in the model tree, those models can be used to create very dedicated graphical user interface for very specific purposes. So you could create, in this example, it's a tank reactor, and you see in the background there, you see the COMSOL user interface with the model tree and with all the turbulent flow, rotating machinery, the boundary conditions, all type of stuff that is required to set up a model. But to use such a model, all this knowledge about the technicalities of mathematical model might not be required. So what you can do as an expert is that you can set up a user interface with just some simple inputs and outputs. In this case, to select different impellers, to select the rotational speed of the impellers, to select concentrations and so on, operating conditions, fluids and so on. But everything else is just set up. So you, as a user, you just click you select the input data and you select the operating conditions, and then you just click the compute button. And so as experts, you can benefit from your work by being able to make very efficient modeling procedures automatically in applications. But you can also share your work, and by sharing, I mean you can sell your work. You can charge for your applications, or if you inside the company, you can distribute your applications for your internal customers, and so that more engineers and scientists within your company can benefit from mathematical modeling. What I didn't show you in this presentation was that there's also a possibility to include external data. And so high fidelity models require high fidelity kinetics and thermodynamic input data. And so you may import this data from Chemkin, NASA, NIST, JANA files. You may also link to other commercial packages for thermodynamics and kinetic data through the so-called Cape Open interface, which is a common interfacing format that can be used for cost simulations. And so the examples that are included in our application library, they're extensive. And this list is of typical applications for the type of simulations described in this presentation. And it's not limited to what traditionally is called the chemical industry, of course. So a classic case for simulating transfer and reaction processes in the field of catalysis and reaction engineering is the monolithic reactor. For example, using catalytic converters. So we have catalytic converters. We also have diesel particulate filters examples that you might use as a starting point for your modeling. And so you can use, well, this figure shows exactly that. So you can use these application library models as a starting point. And this figure shows the simulations of the gas composition in a diesel particle filter or particulate diesel particulate filter. And it also, this model actually also builds up the layer of particles and increases the pressure losses as that layer builds up. And as it heats up, the layer soot starts to be combusted, and then the porosity increases again due to the consumption of the soot particles. In addition of using resources efficiently, we also have a lot of chemical engineers concerned with regeneration and recycling of effluent streams, and that also includes a lot of reaction engineering. And we have such an example also in our application library. Also, a lot of chemical engineers are active in the field of pharmaceuticals and biotechnology, and where drying is a central process. And for pharma and bio applications, freeze drying is a common process, also in the food industry for heat-sensitive products. We have such an example also where water is removed through the sublimation of ice, leaving a porous material when the process is finished. And the production of biochemicals, that's of course where the main community of chemical engineers is, and where a small improvement in the design or in or the process lead to very large benefits or saving in costs. And we have examples of steam reformers, for example, or other endothermic reactions that that occur in tubular reactors or other type of continuous reactors typical for large chemical processes. Emulsions find a wide applications in the production of food, cosmetic, and household products. And the properties and quality of emulsions typically depend on the size and distribution of the droplets, which you can study using the reaction engineering module in combination with the CFD module. Petrochemistry transforms crude oil and natural gas into useful products such as fuels and raw materials. And the polymer industry makes use of the petrochemicals to produce plastic. We have such examples, for example, this multi-jet polymerization reactor. And I also mentioned chemical vapor deposition. And here are two examples of surface reactions, one for a biosensor and one for a CVD reactor, a small unit cell here. And this example is also included in the reaction engineering module, where you have a number of bulk reactions and a number of surface reactions, and the chemistry is described in detail and then pruned in order to treat it in 3 dimensions. And that's done through parameter estimation, of course. We have examples from combustion chemistry, and this is actually a benchmark example of a syngas reaction within a turbulent round jet burner. So this is typically COMSOL, that we have a lot of benchmark examples that you can compare with the scientific literature, and that you can use as a starting point for your simulations. And so with that said, I leave the word over to Jen. Jen?
All right. Thank you, Ed, for these wonderful demos and your presentation today. We received a lot of questions, actually, so we're going to move right along so we can get started with those. So some of the questions that we received dealt with actually coupling different features and different modules together. This first one, how to couple wave optics physics and chemical reaction engineering to model photocatalytic reactions, especially in complex geometries, as this would have a significant memory requirement, correct?
Yeah, that's a good question. I'm not really sure that I can answer that, but in principle, I can answer in a generic way. In principle, you can couple any user interface in COMSOL another one, with any other one, because the basic math engine formulates all the equations from all the physics interfaces and the different modules in the same way, and they're formulated. If you make such a coupling, for example, assume that I don't know this specific example, but assume that you have a photocatalytic reaction and you use the wave optics module or the ray tracing functionality, right, to get some kind of intensity of a certain wavelength. I don't know, but anyway, so that intensity then can be used as a parameter in your reaction kinetics. That's no problem at all, because what COMSOL will do is that it will actually gather all the equations, the contributions in an analytical way, and it will then, from that, discretize to create a numerical model. And you can solve everything fully coupled, or maybe in this case it would actually be maybe sequentially coupled, that you first compute the intensity, for example, and then compute the reactions, and then you go back to the intensity. Maybe you model the wave propagation in the frequency domain, but because that's almost in pseudo steady state compared to the chemical reactions, and then the chemical reactions you model in the time scale, but you have to go back and update, of course, the wave optic problem. So that's certainly possible. When it comes to computing power, then of course, yeah, I mean, that's usually it's not very difficult to formulate a problem in COMSOL that cannot be solved. And what I mean that cannot be solved, because the computer power requires, there's no such computer in the world that can solve it. That's of course easy to create in any modeling package. Yeah. Okay.
All right. So for our next question, the multi-scale interface, is that available in 5.2 or is that new to 5.2a?
Oh, you mean the multi-scale? Yeah, that's new in 5.2a. Yeah. Sorry for that. Yeah.
All right.
Actually, it was possible to model that in 5.2, but then you have to formulate it on your own. You were on your own basically, so it's much improved in this version. But you could do it in 5.2. Okay. Yeah.
All right. So our attendees would also like to know: is there any documentation that specializes in training for using the geometry building features of COMSOL?
Yes, that's a good question. Yes, there are. I don't think they are in the web, or they're not in the set of documentation, but we have courses for geometry and meshing that are specific for building geometries in COMSOL. But we need to improve there. For example, I created this mixer app that does a lot of very complex geometry operations in order to create the impellers, and they're actually all done in COMSOL. There's no CAD packages used, and it's also using the COMSOL geometry kernel. But I will document all of these because they're very complex geometries, and you can actually create pretty complex geometries in COMSOL. Yeah.
All right. So next, can the software model phase transitions, such as evaporation or condensation?
Yes, so the answer is yes, we can model phase transition. We have a couple of examples. Again, that's a subject where we need to exemplify more. We're not very good at exemplifying that. Where a couple of years ago, we had an example of condensation in the headlights of a car. And so we should document that model and provide it. Yeah, but sure, that's possible. Yeah.
Thank you. So during one of your demos, in the setting of species, why do you not change the charge of the species?
Oh, those were not charged, so those were neutral species. But I could very well have set up a reaction with charged species with ions and so on. So we have that's for example, very widely used in the batteries and fuels, so small electric deposition, corrosion, electrochemistry, and plasma modules. Those modules are include very often examples with charged species. Yeah.
All right, this next question involves a general feature. Practically, on your slide from model to app, the feature is good for just small models, right? Imagine a model which needs 30 minutes to run. In such a case, does it make sense to create an app?
Yes, absolutely, definitely. Actually, the mixer in the finest mesh, it takes 3 days to solve, but it's still, I mean, I set up the embedded model behind the app, but I only use the app nowadays because it's so much more efficient. I have programmed the app to automatically perform a lot of operations and sequences of operations that I would have to do with the mouse, you know, clicking with the mouse and so on, and everything is automated. And so, absolutely, there's no limitation. It does not have to be a small app, and that's one of the nice things with the application builder is that you can record a sequence of complex operations like a macro, and then you get that as a method that you record, you know, by running the graphical user interface in the model builder, and you get that as a method, and you can access that method by just adding a button and linking that whole method to a button. So that means that you can run a very complex sequence of operation by just clicking a button. So absolutely, repetitive things, complex things that are error prone are excellent to include in an application, because then you eliminate the risk of the human factor of doing something wrong when in these manual operations. Yeah.
All right, thank you, Ed, for answering all of these questions. Just have a few more slides to tell you a little bit about some of our upcoming events. And also to tell you a little bit about one of the questions that we heard about quite a lot today is about how to try out COMSOL Multiphysics. And one way is to join us at a workshop. Our workshops are free hands-on events where you can meet a COMSOL specialist and try COMSOL Multiphysics with their guidance. Additionally, attend the COMSOL conference, which are 2- and 3-day events available at 7 locations throughout the world. Attend to meet with colleagues and multiphysics simulation experts, expand your knowledge and discover new features through dozens of lectures and hands-on mini courses, and realize your full potential to innovate by using a simulation-driven design workflow. Registration is now open. Go to comsol.com/conference for more information about event dates and destinations. On our website, you'll also find helpful information about multiphysics and our products. And there's more. You can find user stories, a model gallery, the COMSOL blog, and a discussion forum. If you're looking to update your current version of COMSOL Multiphysics or COMSOL Server, or try it out for the first time, go to comsol.com and under the section called Support, select Product Download or Product Update. If you'd like to speak with us directly, just contact us at comsol.com/contact. Well, that's it from us. Thank you, Ed. It's always a pleasure presenting with you. And thank you, everyone, for your attention. I'd just like to turn it back over to Pam to wrap everything up.
Thank you, Jenna. Thank you, everybody.
If you had a question that wasn't answered today, they can send it to me at producer@aiche.org, and I will forward it to Ed and Jennifer. So now, on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Ed Fontes and Jennifer Seggi for this very informative presentation. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this session or to view and sign up for our many others. Goodbye, and we hope to see you again in a webinar soon.